In this video, I wanted to define what a coalition is and how that pertains to determining the bonds-off power for a particular weighted voting system. And I wanted to mention that I'm going to actually jump into 2.2 for a little bit and then go back to 2.1, because in 2.1 in our text, they get into things like what we call veto power and dummy voters and stuff like that. But I think it's easier to analyze those things after we first talked about coalitions. So that's why I'm grouping this into 2.1. Um, and I'll focus more on the bonds-off power distribution in the next lecture module for 2.2. But basically, the way how do we determine the power of a weighted voting system? But basically, the method that it's done is looking at, well, what different groups can form in that system, and how does that affect the outcome, like whether the motion is passed or failed. So, like returning back to the same example where we have four players with weights 7, 5, 4, and 3, and the quota is set to be 10, we could imagine the different groups in which those players could basically vote the same way. And that's the idea of a coalition. It's a group of players voting the same way. Um, and so what we call coalition notation is we use the brackets to describe the weighted voting system as a whole, and to describe basically the subsets or the groups of those players, the ways they form together, we're going to use braces instead. Basically, actually, you can't see my mouse, so let me try to highlight this. Basically, this sort of notation, or make it look like this. So basically, if I'm writing the numbers 7 and 4 in these braces like this is implying that those two players are forming a coalition. Basically, player 1 and player 3. Or, another way that it's written in the book is like this, by writing the player letter number in braces as well. And what this implies is that what we're always going to assume this means is that player 1 and player 2, or sorry, player 1 and player 3 are voting yes. So when we put them in the braces, those are assumed to be yes. And the other implication is that everyone who's not in the group is in the counter coalition, basically the group of players saying no. So when I write this, it also implies that players 5 and 3 are not voting yes. So when we write all this, this is all the meaning behind this, and it's not necessarily intuitive that we would mean this when we were writing coalitions. So a winning coalition is just a coalition in which the group will pass the motion. Or basically, when you add up the weights of those numbers, it's going to make the quota. So in the case of this coalition of 7 and 4, we would call that a winning coalition because they have 11 votes, and if they're both voting yes, they are going to pass the motion, and we know what the outcome will be. And similarly, the inverse coalition, basically the group of players 2 and 4 with votes 5 and 3, would not be a winning coalition, right? Because they only have 8 votes. They're not going to pass the motion. So, and we can kind of imagine that these two are sort of the same situation, but they're not, because when we put them in the coalition, we're assuming these are the ones that are saying yes. So when these two say yes, they will win. When these two say yes, they will lose. And basically, this is a winning coalition because they have enough weight. This is losing because they do not. So another thing that's going to be important as we move into the bonds-off power distribution is to find all of the different groups, because that was just one specific example of just player 1 and player 3. But there's a lot of different ways that those groups of players could actually pass or fail the motion. And in the next example, what I wanted to do is just try to list them all, see if we can find every potential option, and we'll talk about how that is important in a little bit, and why we care about this. But let's go ahead and do this. It says find all the winning coalitions from example 1. Oops, you can't see because I have the wrong window open. Okay, there we go. Find all. Again, I'm going to return back to the packet. And example 1 was just the same group up here. So if we're to find all the winning coalitions, and I also want to talk about how do we do that, like how can we find them all, and what goes into that. But like, for example, we already knew 7 and 4 was 1 because that was in the slides and I was talking about it, but that would be one potential winning coalition. And you can think about, well, what other groups of 2 players could also have enough weight to carry the motion. But basically 7 and 5 would also be enough, right? Because that would be 12, and 7 and 3. And actually 7 with any, player 1 with any of the other players, 7 5s and 4s and 3, all have enough votes. And remember, you only need to you need to make the quota not necessarily exceed it. So when we're looking for winning coalitions, the quota is the focal point, and that's what we're always referencing when we're looking into this. But notice, for example, I'll try to separate these by winning and losing. Um, but for example, 5 and 3 was a losing coalition, and also 7 and 5, the inverse coalition would be 4 and 3 would be losing, and 5 and 4 is another one. Now that one's close because they make 9 votes, but again, you have to make the quota. If you're short, you're losing. But if you're equal to the total weights of the quota, you're good to go. Another thing you might be wondering is, does it have to just be 2 players? And no, coalitions could be of any size, because what we want to do is look at every different possible way this vote could happen. And so basically, these are distinct cases in the realm of possibilities where 2 people say yes and 2 people say no. But of course, 3 people could say yes and 1 could say no. 4 and 0, it could go either way. So what I like to do is start with 2 players, then move to 3 and 4, and kind of just look at each case by case and make sure that I find them all. So let's also look at 3-player groups. So like what I often like to do is start with the first 3 people and kind of go in order. Well, like say for example, you could have 7, 5, and 4. Each of those could say yes, and if all 3 of those players say yes, that's definitely going to be enough votes to make the quota by a pretty big margin. And there could be other situations like 7, 4, and 3. 7. And again, what you could do is pause this video right here or anytime I'm about to start an example and see if you can find them all yourself. And then it's very easy to miss 1 or 2, and that's kind of why I like to discuss this, because this is the most common error that I've seen with my students when they're doing this, is when they're doing the calculations, they just kind of forget about 1 or miss 1, and it's going to throw off all the math later if we don't find them all. But basically, there's also 7, 5, and 3, and there's another one, 5, 4, and 3. And actually, notice that in this case, each of the coalitions with 3 players, they're actually all winning coalitions, because the weights of those, definitely exceed 10 in all combinations. And if you're wondering how would I know that there's going to be 4, this is actually what there's certain math that goes into this that we're not going to actually get too deeply into because I don't think it's necessarily worth it. But note that in a group with 4 players, if we're looking at the situation of groups of 3, since there are 4 players, you could think about, well, there's going to be 4 ways to do that, because you could exclude either player 1, 2, 3, or 4, and those would form 4 unique groups of 3. And that's kind of a general way of thinking about this that can kind of help you with the basics. But anyways, there would be all of the 3-player coalitions would be winning. And also another possibility is what's sometimes called the grand coalition, or the coalition of everybody saying yes, which is like you could also say it's a unanimous decision. Everybody says yes, well then that's kind of a clear-cut decision. Of course it should win when it's unanimous, but that is another option. So basically here we have all of our winning coalitions. Now for losing coalitions, any single player coalition would be losing. So say for example 7 all by themselves, or 5, or 4, or 3. Takes a little bit of practice to write the braces, and sometimes I'm a little bit messy and sloppy when I'm writing them, and also because writing on the tablet doesn't always turn out perfect. And technically, the empty set or the empty coalition is another technical option. But after all is said and done, we could look at literally every different way the vote could happen. 2 players could say yes and 2 could say no. 6 ways that could happen. 3 players could say yes. 1 player could say yes. 0 players or all. And this gives us the total number of coalitions, period. Also, the number of coalitions and this is a formula that's in 2.4, but I'll just reference it right here to show you that this makes sense, is always given by 2 to the nth power, where n is, as I described in a couple videos ago, is the number of players. So basically, if you take 2 and exponentiate it to, sorry, my headset turned itself off as it loves to do. 2 to the 4th power would be 16 but basically 2 times 2 times 2 times 2, and that should give you the number of coalitions in a weighted voting system. But what I wanted you to notice is if you count all these, well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It actually adds up exactly to 16. And basically, there is a way to know, did I find them all? And if you're really obsessed with not missing any, this is something you could consider. Because as I said before, it is important to find all the winning coalitions. If you're missing one or two of them, it will mess up the math later.